Day 41, Honors Physics, Energy, Problem 27. All right, finally we have a more interesting problem. This one's a little more involved. You have this person, child, swinging from point A to point B, the low point in the arc of swing. So A, or these blue dots that I have in my diagram, are the center of gravity, which is the important point to look at. The actual girl or object itself isn't that important, but the point A, the center of gravity, is actually going through an arc that I have in dashed red there, and point B is a little bit lower than point A. But there's the original diagram. Now I have to add to this diagram. So I'm going to pause and do that and explain what I did. Alright, so what I did is I drew a horizontal line from point A using a black dash to the left, which splits up the rope of the swing. The rope of the swing is 4 meters long. Or in other words, if you look at this diagram, I have it labeled X plus H equals 4 meters. I'll leave off the units for now. I'll put that back in. That's just straight up arithmetic, because the two pieces put together have to make the 4 meter length of rope for the swing. The reason why I did that is, well, what's important is we need to know how far this person falls. We're going to use conservation of energy to solve this problem. Transformation of GPE into kinetic energy, with point B being our reference zero level GPE, but our maximum kinetic energy, maximum speed there. As you swing back and forth, your kinetic energy, like for example at point A is where you stop, you have zero kinetic energy but some GPE, that's your maximum GPE, and as you swing from point A to point B, your energy transfers from GPE into kinetic energy with your maximum kinetic energy at point B, minimum GPE at point B. But you fall an effective distance of h. You don't care about the arc, the curved arc. What you care about is how much vertical drop you have when you go from point A to point B, and that's h. Now what you want to look at here is the triangle. I'll redraw the triangle here. It's the part that I call X, the 4 meter string or rope, and that black horizontal dash I have coming across, which I don't care how long that is, but I do know that this is a right angle right here. I'm calling this side X, and I know that the upper angle here is 30 degrees based on the geometry given in the first diagram. So if I know that's 30 degrees, I can use, not 38, that's 30 degrees, cosine of 30 equals the adjacent leg to the 30, which is X, over the hypotenuse, which is 4. So I can solve that for X. So X equals some number. Once I have X, bottom line, what you can see, I hope, is that H, which is the important number over here, H is going to be 4 minus that X, whatever it is. Let's say it's 1 meter. It's not. It's less than 1 meter. Well, then H is going to be some number. That's a little bit less than 4. Well, that's basically what you're going to use to figure out your GPE at point A relative to point B. In other words, what you'll do now is calculate GPE at point A relative to point B, and that's just going to be GPE equals M, I think they give you the M is 20, times 10, times that H you just found over there that I used black marker for. So you'll know what H is. Some number that's slightly less than 1 meter. I don't know, it's probably, well, maybe it is 50 centimeters. I'm not sure what it is, but make sure you keep it in meters. So that'll give you the GPE at point A. Well, what's going to happen is that'll give you an answer then. That answer will then transfer into the kinetic energy at point B, which is going to be 1/2 the mass of the person, which is 20, not 10, 1/2 20 times V squared. So then what you'll do is you take your answer for your GPE at point A and then plug that into your kinetic energy at B, so you'll know the kinetic energy, So you'll know this, and well, that's all you need to know now. And solve for v. Gives you the velocity at point B.